My apologies for that.
That was for the least important part of this, so I'm glad we got that worked out. Thank you. Good afternoon. I'm Max Tynan. I'm DraftKings account manager at AWS. A lot of the sessions you've seen, and you will see it at reInvent, are often led by a member of the AWS technical team, like a product manager, and customers. But today, you'll only be hearing from members of the DraftKings team after I shut up, that is. But that's not the only thing that'll make today unique. It's also the combination of the scale of the problem that DraftKings faced with their Windows application and the fact that they're here to tell that story at all. As their account manager, I've seen firsthand just how focused this team is on building experiences for their customers. So it's been great to see the time that they've put into ensuring that you folks leave with some interesting ideas of your own. So with that, I'd like to welcome the CTO of DraftKings up to the stage to tell you about how you can ensure your applications can handle massive spikes in traffic, what this team affectionately refers to as the Gronk effect.
All right. You guys hear me? Thanks, Max. Thanks for coming here to learn about DraftKings and how we scale our infrastructure to handle our really unique traffic pattern. Excited to walk you through that. So start off, I just want to give you guys a summary of what you're going to get out of today's session. So you've probably heard of auto-scaling groups and elastic infrastructure. It's a big part of what makes AWS so famous and so valuable. And we're going to tell you about how we've sort of adopted some of those capabilities to handle our unique traffic pattern. So a lot of scaling patterns revolve around the strategy of scaling based upon what's coming into your server farm at a particular point in time. So this is on-demand scaling based upon current usage. You can scale things based upon CPU utilization, for instance. And this is sort of built into capabilities right out of the box. But what we're going to talk about today is doing something a little bit different, and it's scaling based upon predicted demand. Not what's happening right now at the moment, but what do you think will happen in 2 hours or 4 hours or whatever amount of time. So before we get into the nitty-gritty of the technical scaling strategies, I wanted to describe a little bit about what DraftKings does, just so you have enough context to understand our problem domain. So DraftKings is a sports media entertainment company, and our primary product is daily fantasy sports. For those who don't know what daily fantasy sports is, the easiest way to describe it is, by way of hands, how many people in the audience play season-long fantasy sports? Oh, great, that's like 100%. So this is going to be pretty easy for me. So daily fantasy sports is like season-long fantasy sports, except we take the whole concept and we shrink it down into a much shorter amount of time. So for football, that would be a week. For NBA, it could be just a day. So you come to the site, you draft, you follow along. You compete against friends or against other DraftKings users, and test your skill and knowledge as a sports fan. And your team accrues points based upon how well the players you selected did in actual real-life events. So that's kind of what's key to sort of the presentation today, is that our users, DraftKings users, are following along with real-life sporting events to get an idea of how their DraftKings team is doing. So what's our scale? Basically, the point of this slide is that DraftKings is at the scale now where we have legit scaling challenges. We can't shove this whole thing on one box and expect it to work. Over the course of 5.5 years, over 8 million registered users have tried out DraftKings. At peak times and on an NFL Sunday, our API will handle over 1 million requests a minute. We do 22,000 entries a minute. So this concept of an entry, it's basically DraftKings selling you a ticket to enter into a contest. Effectively, at the end of the day, that's what DraftKings sells, is tickets into a contest. So these are financial transactions where money is actually exchanging hands. Not too many other places do that volume of financial transactions. It's an SOA-based architecture with over 60 different microservices. So we're not just scaling one sort of monolithic platform here. This is a Windows track session, so I want to kind of tie it back to Windows. DraftKings is primarily based upon the .NET platform. Our back-end systems are written in C#. And I wanted to give you guys a sense of why we chose Windows. Obviously, some pretty subjective material ahead here, but for DraftKings, we feel that the Visual Studio IDE and that development experience really enables our developers with a high amount of efficiency. And the flexibility and power of the C# language itself. C# is a very actively managed and developed language, and that over time has added a lot of different features, both statically typed features, dynamic features, and interestingly, it's actually .NET, the platform, is actually open source now, so it's now a cross-platform platform as well. But probably most important of why DraftKings is a Windows technology company is that the founders knew Windows developers, and I think they very wisely chose to start a company based upon the skill that they could draw from. But that's not to say we're an exclusively Windows-based shop. We are also using a variety of other AWS and other types of language technologies. All right, so that's it for DraftKings, the background. Let's get into sort of the fun stuff. And so, ladies and gentlemen, here is the Gronk effect. And for those of you who don't know, we're a Boston-based company, and the Gronk effect is affectionately named after Rob Gronkowski, who plays for the greatest football team that's ever existed or ever will exist, the New England Patriots. And Rob Gronkowski is famous for two things. One, being a goofball, and two, catching a lot of touchdowns. And after he catches touchdowns, he very dramatically takes the ball and he spikes it in the end zone. And the Gronk effect is named after those spikes. As you can see, this is not a smooth chart. What you're looking at is the DraftKings traffic. This is a CloudWatch chart for our main ELB. So you're looking at our ELB for a Sunday night football game. Does anyone want to take a guess at what those large spikes are? Touchdowns. So what you're seeing is all of our users at Sunday night are watching the same game, and a touchdown occurs, and they all flood into the app to see how that touchdown has influenced their standings in their daily fantasy sports contests. I think someone already answered the second question here of what are those like slightly smaller spikes, and those are the commercial breaks. So this is the traffic pattern that we're trying to scale, and obviously, when your baseline can jump up literally 5x and then come back down minute to minute, you have a unique traffic pattern. So with that, I'm going to invite Eric up, who's our head of site reliability, who's going to tell you how we solve this problem.
Thank you, Jason. Hello, everyone. My name is Eric Bisecker. I'm the Director of Site Reliability at DraftKings. My team is responsible for maintaining the production systems, which it means that we have to deal with the scaling challenge in making sure that all the production systems are at scale to meet this demand. So let me take a minute just to go into this different approaches that we've had to, or different approaches that we review or tried to deal with those large spikes in traffic that Jason mentioned. The option one is we could just keep at a scale that would allow us to serve those traffic spikes. But obviously, that wouldn't be an efficient use of servers, as there's a lot of times when we wouldn't actually need all those EC2 instances in production. The second option would be we would scale as those spikes would occur. So from a demand perspective, as demand goes up, we could reactively scale to meet the needs there. The challenge we have with that is due to the bootstrapping time to turn on new instances and have them be able to serve production traffic, that can lead to a loss of service to our customers as those spikes are very short, in very short amounts of time. So in order to solve those two challenges, we've chosen to go with an approach that allows us to predict what those spikes are going to be in a given amount of time, and then be able to scale up accordingly. So let's review some of the challenges that our scaling approach has to account for. Obviously, the ones that we've talked about right now, for the most part, is the large increases in traffic that we have, where We have to support about a 5x increase in HTTP traffic in about a 2-minute time frame. We also can't leverage a lot of caching solutions because a lot of the content that DraftKings serves its users is very user-specific. So we can't use, let's say, edge caching heavily to be able to address those spikes in traffic. The last challenge we have is that reactive scaling is too slow. We've been able to optimize our scaling approach to be able to take about 6 minutes from when we turn EC2 instances on to when they can start taking customer traffic, which is too slow for those 2-minute spikes in traffic. This chart here showcases that our scaling approach has to also support different types of traffic patterns. On the left, you can see a traffic pattern for our site when baseball contests are going, and you can see on the right the traffic pattern for our website when football contests are going. As you can see, the scale between NFL or football and baseball contests is much different in both the volume and spikes that occur. So our scaling approach has to be able to handle both situations. Here is a chart that shows a correlation between our request count to the website and CPU utilization of our services. The scaling approach that we're trying to do is to predict what that peak is so that we can scale enough EC2 instances to be able to handle that spike and make sure that we don't run out of CPU capacity. So I want to take a minute to go over some of the approaches that DraftKings had used in the past to scale our system. Back a few years ago, when DraftKings had a much smaller technology footprint, it was a very manual process. We had an engineer just spend a few hours turning on new servers and deploying code to them. Obviously, whenever a human's involved, it's error-prone, as well as it's time-consuming to have to do that, and remember to do that for when football contests, remember when the Masters is going on. Like, there's a lot of elements here that could lead to service interruption for our users if done improperly. The next strategy that we tried for scaling was a scheduled approach, where we created a centralized process that would manage the scale-up operations, and it was set on a cron-based trigger. So that actually solved some of the problems of having to have an engineer spend time scaling the system, but we left a lot of money on the table because there was times when we would scale up where we thought we had more servers than we needed, and obviously paying for servers that you don't need is not optimal. It also was not scalable as the number of services grew, as this process had to wait for the servers to come online, deploy them, and as we increased the number of microservers that we had, it took longer and longer for that approach to scale up to the needs that we required. So our solution was a predictive-based scaling approach. It solved the problem of the amount of time that it took to scale up our site. It reduced the cost by scaling only to what we predicted that we would need to scale to. And it was no longer a centralized process, and scaling operations were spread out and controlled by the auto-scaling groups themselves, rather than having a centralized process manage that. All right, so now I want to kind of go into the overall process at a kind of high level about what are the technologies that DraftKings uses to scale or in our predictive-based approach. It consists of 3 steps. In step 1, we have to predict what we think that traffic peak is going to be. Step 2, we have to compute the scaling need, or the compute capacity that we need to be able to handle that predictive scale, or that traffic prediction. And then step 3, we actually need to execute on those computed scaling needs. So in step 1, predict traffic, we have a traffic predictor service that loads data from an Aurora RDS instance, and that traffic predictor will come up with the actual traffic predictions for our max HTTP request rates in different time frames. We then have an Amazon Lambda function that's triggered on a cron, or a CloudWatch event that's a cron-based, which will take those predictions from the traffic predictor and then publish them into our centralized caching solution. At DraftKings, we use Aerospike for a centralized caching solution, and Aerospike is simply an open source key value store. My colleague Frank will actually be coming up after me to discuss how the traffic predictor works in detail. In step 2, compute scaling needs, we have built a .NET web service that we have dubbed NOAA. We felt that that was an appropriate name as it deals with forecasting traffic. And anybody who's familiar with government services knows that NOAA does the same thing. So the NOAA service will read our current production scale and how many EC2 instances we currently have, and that published HTTP traffic prediction that's in Aerospike. It will compute how many servers we need to add for all of our different microservices and publish a custom CloudWatch metric that represents how much we should increase or decrease our scale. Here is a chart in CloudWatch that shows that custom CloudWatch metric that NOAA publishes. When a value of 1 indicates that we are at scale to meet the predicted capacity of the future, a number above 1 indicates what percentage of servers we need to add to be able to handle the predicted traffic. And so like a number in this case for 1.4 would indicate that we need to scale up by 40% to be able to handle the predicted traffic in the future. As those servers come online, NOAA is constantly polling the environment and sees that, okay, we're at scale, everything's good, so that number goes back down to 1. If a prediction comes back that we have too many servers in rotation, that custom CloudWatch metric will dip below 1, and the auto-scaling groups will scale in, and that number will go back up to 1. In step 3 scale out, we use a stepped scaling policy or an auto-scaling groups that actually trigger off of CloudWatch alarms based upon that custom CloudWatch metric that I showed previously. We use a baked AMI approach at DraftKings to scale out our systems. That means that we have created Amazon AMIs that have the DraftKings code pre-installed on them. While that helps us be able to scale out or scale up as fast as possible without having to facilitate deployment when new machines come on, we actually want to make sure that any scaling operation is safe to execute to make sure we don't actually cause a problem in production. So in order to make sure that any scaling operation is safe to execute, we leverage lifecycle hooks on auto-scaling groups. And the way that process works is the auto-scaling group will scale out in EC2 instances. The lifecycle hook will publish a message to an SNS topic. That SNS topic will invoke a Lambda function. That Lambda function will do one of the safety checks. In this case, the most common case, we just want to verify that the version of code on the AMI matches the version of code that's running in production, make sure we don't scale up a bad version or old version of code. That Lambda function will then trigger back to the auto-scaling group, and if, in this case, the versions of code match, then it will tell that auto-scaling group to continue or let that instance scale out. And if that version doesn't match, it will tell the auto-scaling group to cancel the scale up of that instance. This slide just shows how we've actually, some of the configuration details of both the CloudWatch alarm and the auto-scaling policy. Here is a sample of the lifecycle hook and how it's configured on our auto-scaling groups, and a sample message that gets published to the SNS topic from when an instance scales out. As you can see, it includes the name of the auto-scaling group and the instance ID as well. So that helps us be able to validate what the AMI version is that is being used. On this slide is some more details around what this process looks like from an auto-scaling group's perspective. So when one of our auto-scaling groups tells us to scale out or scales out an EC2 instance, since there's that lifecycle hook in place, it puts the instance into this waiting state. The trigger then, through the SNS topic into the Lambda function, will occur. As you can see in the second picture here, in this scenario, the AMI verification failed where the versions of code did not match. And in this case, that Lambda function would then send a message back to the auto-scaling group to tell it to cancel that scaling operation. So you can see the result here is that the EC2 instance was canceled because the versions of code did not match. So kind of in summary of this process, I've kind of shown you how you can take data, predictive data, publish it into Amazon CloudWatch to be able to, and have your auto-scaling groups configured to listen to that CloudWatch metric, and then scale up or down based upon the predictive amount of, the predicted amount of traffic that we're going to have. So with that, I'm going to invite my colleague Frank up, who's going to go over the innards of how that traffic predicting service works. Thank you.
Thank you, Eric. Hi, my name is Frank Lowe. I'm the head of data science at DraftKings. Pretty fun topic to be in. A lot of talk of machine learning so far at AWS so far. Pretty eager to look into SageMaker, I think. See what that is all about. But basically, so data science at DraftKings is a software engineering team that works very closely with data and algorithms in the products that we do build. And we built a component of this broader system, which is the traffic predictor. Let me actually go to the next slide. Sorry, and this over here is a zoomed-in part of the broader design diagram that Eric had talked about. So the traffic predictor we built, the innards of how it works, I'm actually going to cover that in the next slide. I'm going to cover overall at a high level where it fits and where it functions in the broader system. So the traffic predictor itself is a Lambda function. And whenever you invoke the Lambda function, it runs a whole set of data operations that have been predefined that generate out predictions of how much traffic we will have at future points in time up to 12 hours in the future. And so basically, every single time this is triggered, the response is a JSON formatted object that we want to store as state that can be ingested by Noah, which is the scaling service that Eric talked about. And so we need a place to actually store that state. You could store that in S3. You could also put that in a database. We actually put that in Aerospike, which is a schemaless database that's very friendly towards JSON formatted objects. And this Lambda itself is triggered by a CloudWatch event rule. If you don't know what a CloudWatch event rule is, it's basically like a cron tab in the cloud. And it actually plays very, very nicely with Lambda because Lambda is a function in the cloud. CloudWatch event rule is a trigger in the cloud. They work well together. And we set up this CloudWatch event rule to basically invoke this Lambda every 2 minutes. What that means is that every 2 minutes, we are recomputing all of our predictions of how much traffic we will have in the future and updating that state. So like the state itself gets updated every 2 minutes. And when Noah, the scaling service, looks at that state, the maximum it will ever be lagged is 2 minutes behind. So next, I'm going to look a little bit under the hood on how this traffic predictor actually works. I'll offer some context for us. As Jason stated, we have millions of customers. And the way that we actually get traffic is those customers coming in to play fantasy contests that we host on our site. At any given time, we have several hundred fantasy contests. And we want to break things down at a contest level so we can have a granular approach that we can aggregate back up to understand broader traffic patterns. So the first part I want to talk about is like what is the incoming data stream, or what is the data that we care about? One part of the data that we care about is the real-time data that's actually flowing in all the time. And we care about two things. And looking at this at a contest-by-contest level, the two things are position and velocity. What that means is what is the position of a contest is basically how much traffic has come to the contest so far, how many entries it has already received at this point in time. And the velocity of the contest is at this point in time, how fast are the entries coming in? How fast is traffic coming into this contest and people signing up for it, right? The other piece of information that we care about a lot are historical benchmarks. What that means is for every single one of our several hundred fantasy contests that we have on our website at any given time, we've likely run many, many contests that are very similar to it. And if we look at those historical contests that we've run, to come up with a prior belief of the trajectory of the traffic patterns for this current contest that we have that's upcoming. So it's basically like a starting belief. And this is pretty important simply because all of our contests are very different. We run low-stakes contests, mid-stakes, high stakes. And high stakes and low stakes generate traffic patterns in very different ways. We run a lot of different sports where if, like NFL games, because it's a weekly sport, generate traffic over the course of a week, whereas basketball or hockey, because they are daily sports, generate traffic over the course of the day. So they follow very different curves. So it's pretty important that we are pinpoint in our prior beliefs of how every single contest will pace out. Next, we combine that information into a technique known as Kalman filtering. And the actual mathematical details of how this works is kind of nitty-gritty. I won't get down to that level of depth, but I will say at a high level, what a Kalman filter is doing is it starts out with your prior belief of the trajectory of every single contest that we do have, how traffic will flow into it over time. That's like a starting belief, right? But then we're taking constant measurements over time of the position and velocity of contests. This is the thing that runs every 2 minutes. And based on the position and velocity of the contest, we look at that as the state of a contest at a certain time. We also look at previous states of the contest, too. And what we care about most is how this state changes. And what the Kalman filter does is it's a pretty elegant method for combining your prior information with new information that's constantly coming in to update your beliefs at all time on where your contest will be at certain points. So it's basically you're adjusting the curve constantly based on new information. A little bit of backstory about how we actually decided to use Kalman filters here at DraftKings. The lead engineer who designed this system used to actually work with Kalman filters very, very extensively at his previous job. Very different from fantasy sports. His previous job was in helping to design missile guidance technologies. It's a very, very different context. But you'll discover it's a very similar application of Kalman filters. So I'm going to actually step into that example for a little bit. So missile guidance. Say a US Navy ship fires off a cruise missile to try to hit a target that's really far away. At the point that you fire off the missile, you have a path planned. You have a trajectory where you think the target's going to hit. Now imagine that missile is flying through the air at like 1,000 miles per hour. And there's a lot of factors that are going on in real time that can actually affect the trajectory of that missile. For example, like air pressure, or like wind in the sky, or like intricacies around propulsion, things like that, that will cause a target to like veer off course and maybe hit somewhere else, right? So the onboard computer on the cruise missile itself is always making measurements of where is its position at this current time, what is its velocity at this current time, and it's constantly feeding that information through a Kalman filter, merging that with our prior beliefs to have a constantly updated estimation over where the missile will hit. It's actually not even where the missile will hit, but like where the missile will be at different points in the future until it hits. And it's basically updated constantly. So after he left that company, he joined DraftKings and looked at our traffic prediction problem and was like, hey, this actually fits the model really well. Instead of missiles firing off and trying to hit their targets, we can predict your traffic patterns in a very similar way, where like the target you're trying to hit is really how much traffic you're getting at a future point in time. But you can kind of use the same predictive methodology. So if you think about it, like a Kalman filter using its prior beliefs and constantly updated data is able to, on the cruise missile side of things, say that this missile like maybe 30 seconds from now will be at this point. That's a prediction. A minute from now will be at this point, and 2 minutes from now will be at another point. Similarly, you could say that our fantasy contest traffic at like 30 minutes from now will be at this point, an hour from now will be at this point, and 2 hours from now at this point. Very different context, but a similar approach applies. Anecdotally, we know that self-driving cars also use Kalman filters in their path planning, because a car moving forward will have a planned path from the point that it makes that a certain decision. However, as it moves forward, it's taking constant measurements over its like XY trajectory on the road, its velocity, how fast it's moving, to have a constantly updated assumption or estimation on where that car may be, maybe like a half a second in the future, and a second in the future, and 2 seconds in the future. So it's a pretty powerful technique, Kalman filtering. It's one that worked pretty well for us. This next slide, though, is saying that like, while this worked for us, there's a lot of different possible techniques that you could possibly use. The important thing is look at your data, look at your traffic patterns, and find one that really matches your traffic patterns given your industry, your enterprise, your domain. And so Kalman filters worked really well for us because our traffic patterns are very, very event-driven. Those events are sporting events, football games, basketball games, et cetera. And I'll fire off a couple ideas that I have, but basically, if you're in an industry where your traffic is also event-driven, this could also work. So for example, if you're running an auction site, if you're like eBay, you could set up a Kalman filter around every single auction that you do have, and then aggregate that up together. That could possibly work. Or if you're in the business of modeling the volume of financial transactions, like stock trades, or something like that. You could view, say, earnings release as an event where you know that there's going to be a lot of traffic climbing up to that one event, and that could possibly work. Or in the stock trading volume example, there's other models you could choose. The Arch model is also a well-known one that balances pretty well, where you have periods of calmness interspersed with periods of like high activity, so that could work pretty well. Another example I can think of is, well, I used to work in e-commerce before I worked at DraftKings, and I can tell you that those traffic patterns, if you're in e-commerce, say Amazon.com, for example, follow a very predictable and cyclical pattern. So like intra-week, if you look at Sunday, Monday, Tuesday, Wednesday, that traffic pattern, like week over week over week, very, very, very consistent. Even intraday, your noon traffic versus your 3 p.m. traffic versus your 6 p.m. traffic, extremely consistent. So if that is your traffic pattern, you could use some kind of like autoregressive time series model. ARIMA is very popular, and that could probably fit your traffic patterns really well. Another idea I could think of is, let's just say you believe that your traffic is actually dependent on a number of states that are out there. What I mean by that is, let's just say you're in mobile gaming, and you've discovered that people play mobile games less when it's sunny and more when it's rainy, just an example. So you can actually view your traffic as a state. You could view the weather as a state with an incoming feed, and you probably have many, many other states that probably affect your traffic, right? And you could frame that as possibly a hidden Markov model to figure out, to actually estimate how much traffic you will have at a given point in time, given all of your states as they come in. So just some ideas. The whole point of this is there's many ways to do this. Do what makes sense for your business. You can get very analytically creative about how you try to solve these problems. The most important thing is that you find some way to make a prediction, and you find some way to make sure that prediction is constantly updated. And so on to the next slide. Basically, here's a demo of how we actually try to store the prediction results that we do have. This is very straightforward. As I mentioned before, the lambda that we have that actually computes the predictions, it just runs every 2 minutes. And it just creates a JSON formatted object that we store somewhere. Here's an example of the object. Pretty simple. We have estimated traffic at through 12 hours at every single hour. And this is pretty important for us, given that our traffic patterns will tend to be wildly volatile. So it's good to have a forward-looking read on where it will be at different points in time. And this is ingested by Noah. So this is the last slide. So in summary, we are DraftKings. We are the leader in daily fantasy sports. And because our traffic depends on sports games, our traffic can be wildly volatile. So we want to find a better way to get ahead of it. So what we do is we have a traffic prediction algorithm that stores state that's read by a a scaling service that then uses that information to determine how many servers we need to be up to be provisioned at the right size. It means that we're always on the mark. We're never under-provisioned, we're never over-provisioned, but we're trying to operate within the AWS infrastructure as efficiently as possible. So we'll be up here if you have any questions. We'll just be hanging around. Thank you very much.